section 5.5, which is over improper integrals. Improper integrals. That's all we'll be doing in this section. So let's start with an example. Ask you guys to find the following indefinite integral. So this is a throwback all the way to 5.1. Give you guys a second to look at that and figure it out. Pause the video if you need to. Okay, so this is the integral of x to the negative 2 dx. So when we take the indefinite integral, that becomes x to the negative 1, which is negative 2 plus 1, over negative 1 plus c. And so that's minus 1 over x plus c. Alright, so we're going to use that going forward. So remember, the antiderivative of 1 over x squared is minus 1 over x plus c. So now, remember from 5.4, if I ask you to find the area under the graph of 1 over x squared from x equals 1 to x equals 2, then that's going to be given by the definite integral, right? So this will be the integral from 1 to 2, right? We start at 1, we end at 2, of 1 over x squared dx. Right? And what is that? Well, remember, we already found that antiderivative, and we said that it's negative 1 over x. Because this is a definite integral, we don't need the plus c. And that's going from 1 to 2. And what do we get there? Well, that's minus 1/2 minus negative 1 over 1. All right, so what do we really get? It's negative 1/2 plus 1, which is 1/2. All right, so I went through that fairly quickly. Feel free to, rewind the video if you need to. This was something we did in 5.4, right? So we did this definite integral to give us this area here. And notice that what it ended up being was wherever we stopped, here was a 2. That traced over here to this 2, which came down here to be a 1/2. And we ended up subtracting 1/2 from 1. Right, so that's just an observation. Let's look at the next slide here. So this is the exact same setup, but instead of stopping at 2, we're going to stop at 10. So that area is going to go, the integral is going to go from 1 to 10 of 1 over x squared. I could do all the same work that I just did, right? The antiderivative, which we already did, was minus 1 over x, evaluated from 1, and this time we're stopping at x equals 10. So what do we get? We get minus 1 over 10, and then minus negative 1 becomes plus 1, and that is 9 over 10. So when we went all the way out to x equals 10, we ended up with 1 minus 1 over that 10, and we were left with 9/10. So the area under this graph from 1 to 10 is 9 over 10. All right, so see if you guys can start to recognize a pattern here. We'll do one more example to solidify that. So this time, instead of stopping at 10, what if I want to go all the way out to 100? Well, how do I write down that area? Well, that's going to be the integral. I start at 1, I go to 100 of this function, 1 over x squared dx. Now, what is that? Well, we already took this antiderivative. It was minus 1 over x. We're going from 1 to 100, so that's equal to that. When we plug in 100, we get minus 1 over that 100, which, remember, was where we stopped. And then it's going to be minus a negative 1, which is plus 1. So we're left with 1 minus 1/100ths, which is 99 over 100. All right. So do you see the pattern here? Well, let's try, first off, give yourself a second, try to write it down or figure out what's going on, and we'll move on to the next slide where I'll give you that opportunity. So here, what if I want to go from 1 and then just stop at b? I don't know what number b is, but whatever number I stop at, is there a way to write down the area under the graph of this function where I just say I'm going to stop at some x value and we'll call it b? Right, so that's what that looks like, where b could be 5 or 10 trillion, right? We don't really know. We're just saying whatever it is, can I write down the area? Right, so I've given you what that area is as far as a definite integral goes. And I want you guys to pause the video here and write down what this shaded region is, the area under the graph of 1 over x squared from x equals 1 to x equals b. Right? We're using this definite integral here. I want you guys to write it down just like we did before, but instead of 1 to 10 or 1 to 100, we're going from 1 to b. All right, so take a second and do that on your own. Alright, so if you haven't done that, you should pause the video, do it. Assuming that you just unpause the video because you've done it. Let's see what you guys got. Right, so I got, just like before, it's the antiderivative of negative 1 over x. We're going from 1 to b. And so when we plug everything in, we'll get minus 1 over b plus 1. Right, so it's 1 minus 1 over b. Right, so now maybe some of you can guess what I'm going to ask, which is what happens if I let that b run off to infinity? So now we want to say what's the area under the graph for x greater than or equal to 1? Right, I believe that in your notes this might say 0. If you've already printed off the PowerPoint slide or anything like that, because I had a typo when I posted that a while ago, but just change it to a 1. All right, so the area under the graph for all x greater than 1, that means we're going to start at 1 and not stop ever. We're going to keep going all the way to infinity. That's right. Right, so something like that forever and all that area. Right, so the question is that area a number, right? Is it finite or is it infinite? Right? You can have infinite area, but it might also be a finite area even though it goes on for forever. So let's see how we do that. What we're going to do, where we already said if we go from 1 to b, that is 1 minus 1 over b. But if we want to go on forever and not just stop at b, how can we write that? Well, going on forever should maybe remind you of something that we might have done back in chapter 1 called limits. So what we're going to do is say, I'm not going to stop at b, but what I'm going to do is take the limit as b goes to infinity. And this will give me that area. And what that was equal to was the limit as b goes to infinity of this integral, and then we worked it down, and on the last slide we got to that integral is equal to 1 minus 1 over b. And so what is that limit? Well, as b goes to infinity, you get 1 minus 0, which is 1. So the area under the graph of 1 over x squared, starting at 1 and going out forever, is exactly 1. Even though it goes off forever, the area is finite and it's equal to 1. Thinking, oh my gosh, how is this possible? That's really crazy and really awesome, and math is so much fun. Of course, this is the idea of improper integrals. That we can take an integral out to infinity, and it's going to represent the area under the graph out to infinity, but sometimes that area can be finite. Right? And so there are other types of improper integrals. The only one we're going to talk about is a definite integral over what's called an infinite interval. So that just means starting at, like we started at 1 and going to infinity. So that interval goes out to infinity. So this is how we do that, right? This is exactly what we just did, and this is how that is written. If you have the integral, definite integral, we say from a to infinity of f of x, you take, instead of infinity, you're going to drop a b in there and take the limit as b goes to infinity. And the reason we do this is because we can't play with that infinity symbol, right? It's not a number. So instead we're going to use b, which is something we can play with, and then whatever we get to at the end, we'll just take the limit as b goes to infinity. For the sake of completeness, I've put this in here, but you can see that it's just if you're going from negative infinity to b, you're going to put an a where that negative infinity was and take that limit. But we won't actually see any examples like this because we didn't take limits to negative infinity. So this is the big thing we'll be using up here. So, like I said, sometimes that improper integral is a finite number. It's a number. Sometimes it's not, and maybe it could be infinite. Another way of saying that is if you're looking at the area under the graph all the way out to infinity, maybe that area is a finite number. It's a finite area, but maybe it's not. Maybe it's infinite area. And so for these integrals, here's what we say. If this limit exists, then we say that improper interval converges, right? If you take that limit and get a number, then we say that the integral converges. Well, this should say improper integral, not interval. You guys can fix that. Anyway, if this limit converges to a number, if you plug in, or if you take the limit as b goes to infinity and you get a number, then we say that integral converges. If that limit does not exist, then we say it diverges. The integral diverges. So once more, if that limit over here exists, we say the integral converges. If it does not, we say it diverges. Okay, so what these problems will look like is it'll say evaluate or say that the integral is divergent. And I'm going to give you an integral starting somewhere, in this case 1, and going all the way to infinity. Right, so whenever we see this infinity in the integral, we should immediately replace it with a limit. And what we do is we take the limit as b goes to infinity, and then wherever that infinity was, we put a b there instead, and everything else remains the same. 1 over x and a dx. Right, so what we did was we saw this infinity on the inside of this integral, this definite integral. So we replaced it with a b, and we took the limit as b goes to infinity, and those are equal. Right, so we're saying instead of the integral to infinity, we're going to take the integral to b and then send b to infinity. Right, so what do we do from here? Well, we're going to leave this limit symbol out in the front because that's telling us to take the limit, and we're going to evaluate this definite integral just like we would any other definite integral, but the answer will just have a b in it somewhere, and that's okay. Just whenever we get to that final answer, the last step will be to take the limit as b goes to infinity. So here's what that looks like. What is the antiderivative of 1 over x? Well, it's the natural log of the absolute value of x. And since it was the definite integral from 1 to b, we want to evaluate that from 1 to b. And this is that definite integral that I circled in green. And I'm going to rewrite it so I still haven't taken the limit. So I'm going to keep writing the limit as b goes to infinity until I take that limit. And I'm going to rewrite this as just the natural log of, well, what's the absolute value of x when I plug in b? It's just b, since b is positive here going to infinity. And then minus the natural log of 1. The natural log of 1 is 0, so that's 0. So this is just the limit as b goes to infinity of the natural log of b. So whatever that is, that's going to be our answer. So what is it? Well, let's take out your calculator and graph the natural log. What happens as you go off to the right? Well, the natural log function looks something like this when you graph it. And as you go off to the right, this thing blows up to infinity. Right? So that means that this limit does not exist. And since that limit does not exist, this integral diverges. If that limit did exist, and if we got a number, then we would say that this integral converged to whatever number that was. Alright, so this is a property here. We'll box it in blue just for fun. The limit as b goes to infinity of the natural log of b does not exist. That's something we haven't seen before, but I expect you guys to be able to either figure that out from your graph or a table, or if you just... Alright, again, evaluate or say that this integral is divergent. So again, we see an infinity symbol in this integral, so we should immediately replace it with the limit. Instead of having an infinity in the integral, we want to take the limit as b goes to infinity, and wherever that infinity was, put a b. Right, so that replaces that infinity, and then everything else is going to stay the same. 3 to b, and 1 over 2x plus 1. Alright, so how do we find the antiderivative of 1 over 2x plus 1? Well, to do that, we're going to have to do a u substitution. So let's let u be the whole denominator, 2x plus 1. We'll take the derivative of that equation, and the derivative of u with respect to x is equal to 2. And so dx equals du over 2. And we're going to plug all that stuff in just like we used to do in the other sections with u substitution. The only difference here is that we're going to bring this limit as b goes to infinity along for the ride, because we haven't done that yet. And now we've got the definite integral still from 3 to b, and then 1 over, we're going to plug, instead of 2x plus 1, we'll plug in a u, and instead of dx, we have du over 2. So what is the antiderivative of 1 over u du? And then we'll pull out the 1/2. So that's 1/2. Whoops. Look what I did. I started writing, but I forgot to bring my limit symbol along. That's no good, because that's not equal. So you have to remember to bring that along until you actually evaluate the limit. So this is equal to the limit as b goes to infinity of, and now what is the antiderivative? Well, we have a 1/2, and then the antiderivative of 1 over u, just like the last example, is still absolute value, natural log of the absolute value. And then we're evaluating that from 3 to b. So let's plug back in what u equals in terms of x. Again, we're going to have to take the limit as b goes to infinity of 1/2 natural log, and then instead of a u, we have 2x plus 1, evaluated from 3 to b. And what is that? Well, that's the limit, right? We still haven't taken the limit as b goes to infinity. And plug in b, you get 1/2 natural log, absolute value of 2b plus 1, minus 1/2 natural log, and then plugging in a 3, you get 7. 2 times 3 plus 1. So that is what our our definite integral is equal to from 3 to b. Now, letting b run off to infinity, just like before, that means that everything inside this natural log is going to run off to infinity. And just like before, that means that this whole natural log is going to blow up. And multiplying it by 1/2 is not going to slow it down. And subtracting off this number is not going to slow it down. So this limit also does not exist. You could graph this where you plug this into your calculator and look at what happened. Treat b as your variable. Look at what happens as b goes to the right, as the graph goes to the right, b goes to infinity. And you'll see that that does not exist. last example for 5.5. It's a word problem. It says Penny claims that she can make pies at a rate of n of t equals 100 e to the minus 0.5 t pies per year. All right, so this is the rate. It's going to spit out when you put in t equals whatever year, right? So right now it would be t0, next year would be t equals 1. When you plug that in, this spits out the pies per year that she makes, or claims she can make anyway. Now, assuming that her claim is true, and I guess we'll believe her, she was pretty trustworthy, so we'll believe her. It says, how many pies will she eventually be able to produce? All right, so there's two things going on here. One, this eventually, right? So if we're talking about time and we say eventually, that should make you think that time is going to infinity, right? We're saying forever and ever and ever, how long, what eventually, how many will she eventually be able to make? So that means we want to say if you give her unlimited time and you say time goes on forever. The other thing we have going on here is we're asked how many pies. Right, so how do we figure out how many pies? Well, this function n of t gave us the pies per year. It was a rate. And so if we want to figure out how the number of pies has been accumulating, that should make us think that we want a definite integral. So putting all of that together, what do we get? So because we're accumulating, we want the definite integral from what to what. We'll figure that out in a second, but of this function. Right? If we take a definite integral of n of t, which gives the rate of pies per year, then the definite integral will give the accumulation, the total number of pies. If we're starting right now, then that's at time equals 0. And if we're going on eventually, that means we want to go all the way out to infinity. So to get the number of pies, we need a definite integral. Because it says eventually, we're going to start here right now and go all the way out to infinity. So we want the definite integral of from 0 to infinity of n of t. And that will give us the number of pies that she will eventually be able to produce. So now let's work through that. Well, this is the integral from 0 to infinity, and then we'll plug in n of t, so that's 100 e to the minus 0.25 t dt. And now, just like before, whenever we see a definite integral with an infinity symbol in it, we're going to change that to the limit as b goes to infinity and put b where that infinity symbol is. So this is equal to the limit as b goes to infinity, and then we're going to stick a b where that infinity symbol was, and then leave everything else the same. So it's 0 to b, and we still have 100 e to the minus 0.25 t dt. Okay, now we need to find this definite integral from 0 to b. We're going to keep this limit symbol hanging around until we evaluate the limit. That'll be the last step. So we'll have to keep writing limit as b goes to infinity. Now, what is the antiderivative of 100 e to the minus 0.25 t? Well, that's 100. You copy down e to the minus 0.25 t and divide by the minus 0.25. And where are we going? We're going from 0 to b. So we're going to evaluate that from 0 to b. All right, well, what does that equal to? We still have the limit as b goes to infinity. Now, what is 100 divided by minus 0.25? You can either plug that into your calculator or realize here that minus 0.25 is negative 1/4. So dividing by a fraction, multiply instead by the reciprocal, which reciprocal of 1/4 is 4. So that gives us minus 400. So that's 100 over minus 0.25. E to the minus 0.25t, evaluated from 0 to b. So again, that 400 was just taking the 100 and dividing by minus 0.25. And now, let's plug in b and 0 and take the difference. So it's the limit as b goes to infinity of minus 400 e to the minus 0.25b. So that's plugging in b. And we need to then subtract plugging in 0. So when we plug in 0, we get minus 400 e to the minus 0.25 times 0. So that's just e to the 0. But anything to the 0 is just 1. So we don't need to write e to the 0. We can just write times 1 or not write anything. So now, what is that? Well, our minus signs cancel, and this is now 100. Sorry, not 100. 400 as a positive, so plus 400. And now we need to know what happens as b goes to infinity. So I'm going to rewrite this just to help us see that. So this is minus 400, and then e to the minus 0.25b is the same as over e to the 0.25b, and then this is plus 400 here. So what happens to e to the 0.25b as b gets bigger and bigger and bigger and bigger and bigger? Well, that's just e to the bigger and bigger and bigger and bigger numbers, and e to the whatever is just going to keep blowing up. And that's going to force this whole term here to go to 0 when you take that limit. So this is 0 plus 400, which is 400. Alright, so that is how many pies Penny will eventually be able to produce. 400. One thing here is, again, we took the limit of something we have not taken the limit of before. And what's important is just that if you look at the graph of e to the x, it looks something like this. And so if you go off to the right forever, it's going to blow up. And if you look at e to the negative x, it's 5. There's your homework. And there is baby Sully when he could barely get onto the bed by himself.